Hi, my name is Alexander Bulekov, and today I'm excited to present to you Saphire, a system for sandboxing PHP applications at the level of system calls. This work was done at Boston University with my co-authors Rasoul, Jahanshahi, and Professor Manuel Egele. PHP is a scripting language that is tailored specifically for developing web apps. Since its appearance in the 90s, PHP has gained quite a lot of traction, with W3Techs estimating that it powers close to 80% of dynamic websites. Moreover, PHP has become the language of choice for developing versatile content management systems, or CMSs. These include WordPress and Drupal, which power a large fraction of the web on their own. In fact, WordPress is estimated to run 40% of websites today. It comes as no surprise that the security of the PHP web app ecosystem is an integral component of web security as a whole. Sadly, remote code execution vulnerabilities, or RCEs, are a major and tangible threat to web apps today. Year after year, we see reports that RCEs are the most common and most critical vulnerability for content management systems. The problem doesn't just stop there either. Individual websites customize their CMS deployments with additional plugins to provide unique experiences to their users. Unfortunately, these plugins multiply the amount of potentially vulnerable code ripe for RCE exploitation. As such, a remote code execution vulnerability in a single CMS or even in a single CMS plugin can lead to hundreds of thousands of compromised hosts. Everyone knows this is a big problem. In fact, the Sororium initiative recently tripled their payouts for WordPress exploits to $300,000. So how can we improve the situation? While it is important to invest time into proactively locating and patching buggy PHP code, it's also crucial to provide dynamic protection to web servers running potentially vulnerable web apps. Now, for native software, in addition to hardware-level defenses such as non-executable memory, mitigations at the software OS or Syscall interface have gained widespread adoption in the last years. Essentially, developers have recognized that exploits are of limited utility if attackers are unable to invoke dangerous syscalls and gain additional access to sensitive resources on the system. On Linux, there's a dedicated seccomp feature that allows programs to give up future access to syscalls that the software doesn't need. This technique has been used to filter unneeded syscalls for a wide range of software, including web browsers, hypervisors, and containers. On OpenBSD, there's a simple facility called Pledge, which is used to filter syscalls on close to 70% of packages. So why aren't we doing the same thing to mitigate RCE attacks on web applications? Well, unfortunately, if we try to implement this, we quickly run into a problem. A native program can usually tell which syscalls it will invoke in the future, since code in the binary or its libraries directly invokes the syscall. However, if we look at a PHP script, it has no concept of syscalls. A PHP developer who wants to access a sensitive resource such as the disk or the network has to call into the PHP API. Essentially, the details of the software OS interface are abstracted away within the PHP's interpreter. Scripts simply call into API functions which are implemented in the interpreter's native code. Without additional information, the lines in a PHP source file cannot tell us anything about which syscalls will be invoked while running the script. In fact, even though some PHP APIs share a name with libc functions, they can have vastly different behavior. For example, the call to fopen here will actually initiate an HTTP connection using system calls like socket. You certainly can't do that with libc's fopen. So it's clear that we cannot filter syscalls by only looking at the high-level code in PHP scripts. Maybe instead we should look at the PHP interpreter. Well, the interpreter is designed to invoke any syscall that could be required by any PHP script, including ones used to mount disks or shut down the machine. So if we just look at all of the syscalls referenced in the PHP interpreter's native code, we will come up with a weak syscall filter which won't provide any meaningful protection against exploits. To address these difficulties, we built Saphire, which is our system to automatically formulate restrictive syscall filters for individual scripts in a PHP application. We can apply these filters to a live web app to limit the potential damage of an RCE attack. Saphire is split up into 3 stages. In the first 2 stages, we independently analyze the PHP interpreter and the PHP application that we wish to protect. We combine the results, and in the 3rd stage, we leverage Linux seccomp to filter syscalls invoked by a live PHP web app. The first 2 stages are done completely offline, and only the 3rd stage is active while the web app is running. Now let's look at this in more detail. In the first stage, we are focused on the PHP APIs implemented in the interpreter's native code and exposed to the high-level PHP scripts. Specifically, for each API, we want to identify the set of syscalls that the API might invoke. To do this, Saphire starts off by performing a static analysis over the interpreter binary and its libraries to get a base mapping of API functions to syscalls. To refine this mapping, we take advantage of PHP's extensive unit tests. Essentially, we run through the test suite and monitor the syscalls invoked by the interpreter. By examining the interpreter's internal state, we can associate each syscall with the API function that invoked it. As there are a lot of moving parts here, we describe our stage 1 analysis in far more detail in the paper. By merging the results of the static and dynamic components of our analysis, we get our stage 1 result, a mapping of PHP APIs to syscalls. In the second stage, we are dealing with the actual PHP applications, and specifically, we are interested in associating each script with the set of PHP APIs that it might call into. To do this, Saphire relies on a static analysis of the PHP code. As with stage 1, the full details are included in the paper, but essentially, there are two main components to our analysis. The first component identifies PHP APIs, which are referenced directly within the code of each script. However, because PHP supports including additional scripts within the code, a script might end up calling into APIs that are not mentioned anywhere in its own source code. Since these APIs run within the same interpreter context as the main script, they must also be considered when building a syscall filter. So to do that, we built our second component, which identifies dependencies between PHP scripts. Since PHP code is highly dynamic, our analysis relies on a lightweight form of constant folding to resolve include paths. By traversing the resulting dependency graph and associating each script with the PHP APIs called directly within its code, we produce our stage 2 result, which is a mapping of PHP scripts to the PHP APIs called within their code, or by their dependencies. So from stage 1, we have a mapping of PHP APIs to syscalls. And from stage 2, we have a mapping of scripts to PHP APIs. Combining these, we get a third mapping associating PHP scripts with the syscalls that they might invoke. This final mapping also acts as a set of filters that we use to determine which syscalls are needed to execute each script. So in stage 3, we are ready to take our site online. Saphire provides a PHP extension to enforce the syscall filters. When a new PHP interpreter is fired up to execute a script, Saphire's extension kicks in and it loads the syscall filter corresponding to the script that is about to run. Saphire applies this filter using seccomp. Then, the interpreter proceeds to execute the script. At this point, Saphire's job is actually done, since the Linux kernel takes care of allowing or blocking syscalls. If the kernel receives a syscall that is blocked by the filter, it simply kills the interpreter process, putting an early stop to a potential attack. We evaluated Saphire over vulnerable versions of 6 popular web apps. At the beginning of my presentation, I mentioned that content management systems are often extended with plugins. To capture this phenomenon within our evaluation, we added 9 buggy plugins to our deployment of WordPress. Finally, we obtained 22 of the most recent public RCE exploits for our web apps and plugins. As a first step, we quantified the reduction in attack surface due to Saphire's protection. By examining the sizes of the syscall filters, we found that, on average, Saphire reduces the number of accessible syscalls by 80%. In these graphs, each script in the web app is represented by a value on the x-axis, and the syscalls are on the y-axis. This whole space above the orange area represents syscalls that are blocked by Saphire's filters. Since there are hundreds of syscalls, and it's often not clear what security risks are associated with each of them, we also looked at the set of well-known dangerous syscalls, as defined in Bernaschi et al. These syscalls range from ones used to open files to ones used to run executables and mount disks. We found that among the set of dangerous system calls, Saphire also blocks 80%. The dangerous syscalls that are allowed by Saphire are in the red region at the bottom of each of these graphs, whereas the blocked ones are in the dark red at the very top. While that provides a quantitative measure of the number of syscalls filtered by Saphire, from that data alone, it's not really clear whether these filters are actually effective in blocking real exploits. So to address that, we ran the 22 exploits in our dataset against web apps protected by Saphire. We found that Saphire blocked every exploit in our dataset. But we should keep in mind that a good protection system doesn't hamper the experience of benign users by falsely blocking requests. So to measure the risk of false positives, we ran an evaluation featuring an ensemble of automated and manual testing and crawling techniques. we found that Saphire only triggers a few false positives in one of our web apps. And that is due to the peculiar way that Joomla registers some classes with dynamically generated names. That edge case was not covered by our static analysis in stage 2. But this table actually presents the data for Saphire's most restrictive configuration. In practice, we can run a more conservative static analysis, which avoids this false positive at the cost of slightly larger syscall profiles. See the paper for more details about that. We also looked at the dangerous syscalls available for exploits and found that they are mostly limited to simple file operations. Finally, request latency is critical on the web, and protection systems are useless if they impose too high of a performance penalty. Now, a naive deployment of Saphire only uses a PHP interpreter instance to process a single web request. In the real world, web servers often reuse PHP processes for hundreds of requests. Just turning off that optimization results in a pretty serious drop to performance. However, using features already present in web servers, we were able to easily run Saphire in a configuration where processes protected by our plugin can be reused for many requests. We provide details about how we did that in the paper, but in the recommended setup, our prototype implementation of Saphire incurs less than 2% overhead across the board for both Apache and Nginx. In summary, we found that syscall filtering mechanisms that have gained traction in the past years are also applicable to interpreted scripts. However, building an effective profile requires careful consideration of both the scripts and the underlying interpreter. It's not enough to just look at the native web server when we are trying to address RCE vulnerabilities hidden deep within interpreted code. We built Saphire as a solution for filtering syscalls at the granularity of individual PHP scripts, and found that it is effective at defeating real-world exploits without impacting normal users. Since we are using the same underlying syscall filtering tech as native apps, Saphire incurs a low overhead. Our artifacts were evaluated and we just released them. If you enjoyed our talk, please check out our paper as well. Thank you for listening.